Okay, so the idea would be, suppose you've solved your Schrodinger equation or whatever it is you need to solve to figure out some set of eigenstates. And I could, if I want to be a little more precise, I could put a little superscript 0 here, but I guess it'd be a pain to keep writing that down all the time. And so this would be the thing, let's say you've already solved it. Okay, this is for the particle box. Each in the wave function representation. Oh, let me just remind you, wave function. I'm just going to remind you one more time, a wave function, you can think of that as being the projection of your state, let's say, of any state, this could be the size of n or whatever state it is, onto the state in which the particle is at position x. And so that's a way of, another way of thinking about your wave function. And then if the complex conjugate of that guy would be kind of doing it in the other direction, like this. And then finally, if I was to say, oh, what is this guy right here? Inner product between any two arbitrary states. They don't have to be eigenfunctions. They could just be some arbitrary states. Well, this is where I could actually, let me see what happens if I put that identity operator inside here. Because that, like this, but using the weight in the x representation of that. So that would be phi integral dx, and then outer product x psi. And then if you look at this okay, I'll pull this guy outside here. So you have integral dx phi x psi. And notice that now that just becomes what you're used to seeing before, hopefully. So that just becomes integral dx phi star of x psi of x. And okay, and so at any rate, in the wave function representation for the particle box, these would be the guys that we said before were something like square root of 2 over L times sine of n pi x over L, something like that, in the wave function representation of those states for the eigenfunctions. I wonder if this thing will come back on here. So now the idea, okay, so by the way, this would be the, let's say in the case of the particle box, that would be the original Hamiltonian that had the square rail potential and just a nice little flat bottom with nothing else in there. Now the idea is that, okay, now I'm going to throw in the nastiness. Maybe I'll figure out some homework assignment where hopefully it'll be doable and maybe not too nasty. At any rate, this is where we throw in a little nastiness. Now we can finally see it over here. So we say, okay, now we're going to go ahead, we're going to throw in this other guy right here. And a lot of times that might just be another added perturbation to the potential or added piece of potential that really throws a monkey wrench in the works. Okay, there we go. So the idea is, okay, we add this extra piece, and most of the time that'll be another potential, like in the particle box would be, oh, somebody threw in some other little piece that looks like that at the bottom of your potential well. And so that's this guy right here. And then pointing out that, okay, this is the original basis state. Again, I could have put a superscript 0 to be a little bit more explicit about it. I just got sick and tired. I didn't want to keep having to write all that stuff in there. So just remember that these are the original eigenstates right here in terms of the original basis states for the original Hamiltonian, which is this guy here. So these original basis states, okay, they're orthonormal. That means they satisfy this relationship right here. And then any arbitrary state can be written like this, where each of these coefficients is this guy. And remember, I was able to get that same result using that funny other representation for the identity operator. And then we could say, okay, now, what I did in these notes is I said, okay, I don't want to do an n by n, nasty problem, diagonalization problem. So what I did is say, well, let's try to simplify it, and just suppose we were just to look at the bottom two eigenstates in this case. And so what we did is we said, okay, suppose that in the presence of this extra piece of the Hamiltonian, like extra perturbing potential, I now express the states which we don't know what they are yet. So there's going to be two of these guys. In other words, there's going to be, for the two-level system, you're going to have two new states. These are unknown. We don't know what these are. That means we don't know what these coefficients are. And by the way, these are just labels that I said, okay, I'm going to write this. By the way, there'll be two of them. One of them is called psi plus. The other one's called psi plus. The other one's called phi minus. And so phi plus would be C1 plus times this guy plus C2 plus times this guy right here. This is just some notation that I decided to use right here in this case. And phi minus would be C1 minus, an unknown coefficient that we don't know what it is yet, times this guy plus C2 minus times this guy. So we don't know yet what these coefficients are. And now the idea is that, okay, the full Hamiltonian, so now this is the full Hamiltonian, H naught plus H prime right here. Operating on these guys, we wanted to give new energy eigenvalues, which I labeled. I give them some new labels that is called E plus and E minus right here. And so they're going to be they'll somehow be related to the old energy eigenvalues, E1 and E2. And so now we do a bit of algebra. We say, okay, I'll rewrite it like this, H minus, I'll pull this to the other side of the equation. This is tricky because here we have something which we have to be a little careful because that's a number right there, and this is an operator. So how would you handle that if you were to be a little bit more rigorous? What you do typically would be to multiply that number by another way of writing an identity. I should have probably put an identity operator here, where in that case the identity operator would just be a row of ones going down the diagonal and a bunch of zeros in the off diagonal. So to be a little bit more precise, I probably should have put a little identity where that's that diagonal matrix with the ones going down and the zeros. So that way both of these could be thought of as some form of matrix. At any rate, so hopefully, but that's the basic, that's more or less the idea then. And so now, okay, in terms of the original basis states, that would be something like this. And now what we do is I say, okay, let's express it somehow in matrix form. Oops, okay, okay, well here's just where I write down the matrix elements for the Hamiltonian. So here's where the things also start to get somewhat non-trivial, and the idea is that, okay, originally, for the original Hamiltonian H naught, remember that this guy was diagonal originally. If I just had the original Hamiltonian H naught right here. Okay, now, when I put in this extra piece, H naught plus H prime, and plug it into here, now this thing actually will have non-vanishing off-diagonal elements. So that means that some of these guys, so even the off-diagonal elements here will not be zero. And by the way, this actually doesn't have to be in the limit where these are necessarily small compared to the others, as long as I'm in that so-called, if I can somehow justify taking that two-level approximation. Now, some cases where it is a nice, perfect two-level system, this would actually end up being exact, actually, if you just had a perfect two-level system. And so in matrix form, what this looks like is something like this. So we end up, the equation which I obscured that was up here, I hope you can remember, we had the H hat minus E times some other stuff is equal to 0. So it ends up looking like this in matrix form. So in matrix form, by the way, it's going to be it's actually really two separate matrix equations. Think of it separately for the E plus and the pluses here, and then and then another separate equation for where you have the minus right here. So it's really two sets of matrix equations that are just sort of compressed into one.
You just have two eigenvalues, or two eigenvalues.
Yeah, because there'll be two different eigenvalues for the e's right here, and then two sets of coefficients also here. Okay, and so now this is where I totally forgot the proof of how you prove that, but just something I vaguely remember from matrix linear algebra is that whenever you have this kind of equation like this in linear algebra, so let's say we focus this on the plus, okay, right here, then in order to have a solution, that's when you have to say, well, the determinant of this matrix has to be equal to 0, basically. And you know that probably can prove it better than I can, in other words. So this is where we say, okay, in order for this thing to have a solution,
Can I find the characteristic equation?
Yeah.
is that what it's called? I guess. So at any rate, okay, so maybe, okay, so at any rate, okay, so this matrix equation has a solution if the determinant, maybe if and only if, I suppose,